Welcome to Lab 3, Black Hole Lab. The objective is to analyze the motion of a star and find the net force on the star for all points in the given dataset. Using the results of your analysis, estimate the mass of the black hole. The assumptions we start with is that we assume that the net force on the star is due to a black hole located at the x component negative 2e to the 10th, the y component 1e to the 10th, and the z component 0. Assume that the net force on the system is due solely to the gravitational force of the black hole, and we are given that the star has a mass of 1.989 e to the 27th kilograms, and the time step is 1 Earth day, which has 86,400 seconds. We use Newton's second law and the momentum principle along with the Python starter program to build a model for the net force by the black hole on the observed star. We then plug all of our known values into the gravitational force equation and solve for the unknown, which is the mass of the black hole. When we look at our program, we plug in the origin, which is the black hole. We plug in the star's mass, the time step, and we incorporate the index so that the program knows which x and y components to use for the program. We also plug in the equations or programs for finding the final and initial velocities, the final and initial momentums here, the change in velocity and the change in momentum, and our F-net is the change in momentum divided by the change in time, and that also has its parallel and perpendicular components. We have the program print out the time and the magnitude of the F-net force. When we run our model, the blue arrow is the perpendicular force to the motion, the yellow arrow is the net force, and the black arrow is the parallel component of the force. Here we have the net force, which is printed out at the end of the program, and the perpendicular and parallel components. After extracting the net force at each day along the path of the star, we plugged our numbers into the gravity equation, which is the F-net force equals the gravitational constant times the mass of the star times the mass of the black hole divided by the distance between the two squared. Our numbers at the final position here in our program, the F-net force was equal to 3.0256 e to the 24th. The gravitational constant is the same. The mass of the star equals 1.98 times 10 to the 27th. The position here is from the position of the star minus the magnitude of the position comes from the Pythagorean theorem incorporated with the position r. The solution, we plug all of our known values into the gravitational equation and solve for the mass of the black hole, which we got to be 2.376 times 10 to the 31. Remember, this is an estimation because dp over dt is an estimation of the change in momentum over the change in time. Also remember that the numbers we used for g as well as our position points were not exact, so there may be slight incongruities between our estimated mass of the black hole and the real mass of the black hole. We would calculate the mass of the new black hole to be the same as the first black hole because we are finding the mass based on the motion of the star, and that does not change. F-net and F-net parallel as well as F-net perpendicular have equal values to their counterparts, the change in momentum divided by the change in time and its parallel and perpendicular components. However, it is important to remember that F-nets are the causes and the change in momentum over the change in time are effects. So although they have the same values, they are different because one is a cause and one is an effect. In conclusion, we are able to estimate the mass of the black hole by extracting the net force from position data using Newton's second law and the momentum principle. We then use the theory of gravitation and the equation F-net equals g times mass of the star times mass of the black hole divided by the position between the two squared. to solve for the mass of the black hole. We emphasize that this is an estimation because dp over dt is an estimation of the change in momentum over the change in time, and the numbers are also estimations. Thank you for watching Lab 3.